Welcome to a lesson on evaluating double integrals. If we have a double integral in this form here, we integrate with respect to y first, and then integrate with respect to x. But if it's in this form, we integrate with respect to x first, and then with respect to y. And if we're integrating with respect to x, we treat y as a constant. And if we integrate with respect to y, we treat x as a constant. Let's try some of these. Here we want to evaluate the integral, but we also want to sketch the region of integration. So since we're first integrating with respect to y will be on the closed interval from 1 to 2, and x will be on the interval from 0 to 2. Let's go ahead and sketch this region. X is between 0 and 2, and y is between 1 and 2. So we would have the rectangular region that looks like this. This is our region of integration. X is on the closed interval from 0 to 2, and y is on the closed interval from 1 to 2. So now we're going to integrate with respect to y, treating x as a constant. So we'll have y squared over 2 minus 3x squared is a constant, so we'd have minus 3x squared y. Limits of integration are from 1 to 2. Now because we integrate with respect to y, we're going to replace y with the values of 2 and 1. So when y is 2, we'll have 2 squared divided by 2, that's 2, minus 3x squared times 2, that's 6x squared. And now we'll replace y with 1, we'll have 1 half, and here we'll have minus 3x squared. So we'll have 2 minus 1 half, that's 3 halves, and then negative 6x squared minus a negative 3x squared, that'll be minus 3x squared. And now we're going to integrate this with respect to x. So we'll have 3 halves x, this will be minus 3 times 3 squared over 3, or minus x to the third. We're going to evaluate this at 0 and 2. So when x is 2, we'll have 3 minus, this is going to be 8. And when x is 0, both of these are 0, so we have 3 minus 8, so this is equal to negative 5. Remember, a double integral only gives us the volume when the surface is non-negative in the region defined here in blue. Let's take a look at another example. Because we have dy here, we know that y is in the closed interval from 0 to x, and x is on the closed interval from 0 to 1. Looks like we have a triangular region here. X is between 0 and 1, but y is between 0 and x. So if we were to graph y is less than or equal to x, that's a line with a slope of 1 passing through the origin. And since the maximum value of x is 1, the maximum value for y would also be 1, so it stops here. So our region of integration is when x is in the interval from 0 to 1 and y is in the interval from 0 to x. So it's this triangular region here. So now we'll integrate with respect to y, treating x as a constant. So we'll have the integral from 0 to 1 of just y times the quantity 1 minus x squared to the 1/2 power. Limits of integration are from 0 to x. And again, because we integrate with respect to y, we're replacing y with x and 0. So when we replace y with x, we're going to have x times the quantity 1 minus x squared to the 1/2. And then when y is 0, this product would be 0. So now we just need to integrate with respect to x. Well, this is going to require u substitution. U is going to be equal to 1 minus x squared. So du is going to be equal to negative x dx. Notice our integrand does contain x dx, so I'm going to go ahead and divide this by negative 2. Let's go ahead and rewrite this in terms of u. X dx is replaced with negative 1/2 du. And all of this is u, so we have u to the 1/2. So when we integrate this, we're going to have negative 1/2 times u to the 3/2 divided by 3/2. But dividing by 3/2 is the same as multiplying by 2/3. And then u is actually 1 minus x squared. So we need to evaluate this at our limits of integration. Before we do that, we can see this simplifies nicely. So we have negative 1/3 times this quantity. Let's go ahead and evaluate this on the next slide. Okay, so when x is 1, we're going to have 1 minus 1 here, so that's going to be 0. And then when x is 0, we'll have 1 to the 3/2, so that's just going to give us 1. So we have negative 1/3 times a negative 1, so this gives us a positive 1/3. And let's go ahead and take a look at one more example. Here we're going to integrate with respect to x first. So we'll have x to the 4th over 4. And our limits of integration are 4 cosine y and 0. We've seen this a couple times before. Notice if we integrate with respect to x, if the limits of integration are in terms of functions, they must be in terms of y. So we're going to replace x with 4 cosine y. Well, 4 to the 4th divided by 4 is going to be 4 to the 3rd, which will give us 64. And then we have cosine to the 4th y. And then when x is 0, this would be 0 again. And now we need to integrate this. Let's go ahead and factor out the 64. To integrate this, we could use a power-reducing formula, but we could also recognize that since the limits of integration are from 0 to pi over 2, and we have an even power of cosine, we could apply Wallace's formula, which tells us if we have cosine to the power of n, where n is even, and our limits of integration are from 0 to pi over 2, this is going to equal 1/2 times 3/4 times 4/5 all the way to n minus 1 over n times pi over 2. So for our integral, we have n equal to 4. So we're going to have 64 times 1/2 times 3/4. And now we're going to stop because if n is 4, the last fraction would be n minus 1 over n, or 3/4, and then times pi over 2. And this simplifies very nicely because 2 times 4 times 2, that'd be 16. And there are 4 factors of 16 in 64. So we're left with 4 times 3 times pi, or 12 pi. And so Wallace's formula saves us quite a bit of time in this problem rather than using the power-reducing formulas. I hope you found these examples helpful. Thank you for watching.